Look out into the solar system, and Mars stands out as the most obvious candidate for a second human home. It has a day that is almost exactly 24 hours long, polar S-caps, and familiar sweeping topography. And while Mars is only half the diameter of Earth, this map-based data visualization, stripping away Earth's oceans, reveals something surprising. The total amount of dry, walkable land on both planets is exactly the same. These striking similarities, however, exist only on the surface. To find out why the planets followed such different paths, we have to look at the massive hidden engines that actually drive a world's habitability. Down on the ground, Mars is an irradiated, barren desert with a lethal average temperature of -63 degrees Celsius. This volumetric comparison chart highlights the extreme contrast between the planets. Earth's dense layer of nitrogen and oxygen is over 100 times thicker than the thin atmosphere surrounding Mars. Worse, that tiny fraction of Martian air is toxic, composed of 96% carbon dioxide. Surviving here necessitates the artificial reconstruction of the massive geophysical environments that Earth maintains naturally. To understand what makes a planet habitable, we have to look deep underground. A world's surface conditions are heavily dictated by an immense thermal engine hidden inside its core. Deep inside Earth, circulating liquid metal acts like a giant dynamo, projecting a protective magnetic force field into space. Mars had a similar structure, but its heat radiated away faster. Its core solidified, the engine stalled, and the magnetic force field vanished. Without that shield, a rocky world has absolutely no defense against the harsh environment of deep space. Moving up to the crust, that same internal heat also drives plate tectonics and volcanoes, which act as an exhaust system to pump out atmospheric gases. Evidence of a highly active early Mars is carved directly into the rock. It hosts Olympus Mons, the single largest volcano in the entire solar system. Billions of years ago, massive geological structures like this vented heavy exhaust, covering early Mars in a thick, warm, and wet atmosphere. But as the core froze and the engine stopped, this geological exhaust system completely shut down. The last major volcanic activity on Mars fizzled out roughly 500 million years ago. With a dead core, the planet lost its natural ability to produce new atmospheric gases to replace whatever it lost, and it was losing gas fast. The primary threat to any planetary atmosphere is the solar wind, a relentless stream of highly energetic, charged particles flowing directly from the sun. Earth's magnetic shield successfully deflects these charged particles, allowing our thick, life-sustaining atmosphere to stay safely nestled against the crust. Without its own magnetic force field, Mars had no way to block the impact. The solar wind slammed directly into its unprotected atmosphere. Because the young sun was highly energetic, these incoming particles quickly stripped the thick Martian air away, blowing it into deep space in only a few 100 million years. The relentless mechanics of the solar system essentially dismantled the Martian life support system, leaving behind the cold, thin-aired desert we see today. To inhabit Mars, we have to reverse engineer the planet. We must simultaneously artificially thicken the atmosphere and find a way to trap solar heat. One realistic engineering solution involves manufacturing highly specialized greenhouse gases on the surface and pumping them out to aggressively trap incoming solar radiation. We could also import an atmosphere. Using thermonuclear rockets, we might transport large bodies of ice packed with water and carbon dioxide from the distant Kuiper Belt directly to Mars. Rapidly raising the atmospheric pressure through imported carbon dioxide and water is the absolute baseline requirement. Until the pressure rises, introducing biological life is impossible. Once conditions stabilize, the next phase is seeding the planet with hardy, genetically modified microbes designed specifically to survive the harsh rock. This biological payload serves a vital function. Over generations, these microbes inhale the toxic carbon dioxide and exhale the breathable oxygen required for higher animal life. Successfully terraforming Mars requires brute forcing a dead planet, artificially replacing its broken engine and shattered shield through sheer technological power. But attempting to revive a dead world highlights how perfectly calibrated our own planet is. It forces us to recognize the incredibly fragile geophysical systems required to keep Earth alive.